Hey, in this tutorial we're looking at section 8.7 on integrals involving partial fractions. Okay, so if the derivative of ax squared plus bx plus c equals 2ax plus b, then the integral of 2ax plus b on ax squared plus bx plus c with respect to x equals log to the base e of the modulus of ax squared plus bx plus c. Okay, we can also use partial fractions to simplify functions before integration occurs. Okay, so what we're going to do is we're going to factorise our denominator, okay, and then split our numerator into two parts. We're calling A and B. Okay, and then what we're going to do is we can cross multiply and go through the process of our partial fractions to find A and B to be able to then integrate our two parts separately. Okay, so I've got a worked example showing this process. This is worked example 33. So we need to integrate 12 on 36 minus x squared. So the first thing we need to do is realise that we can write our 12 over our 36 minus x squared. Well, if we factorise that, we're going to get 6 plus x and 6 minus x. Oh, sorry, we need to worry about dx at the moment. Great, so what that means is we can split these up and say, well, we've got some numerator a over 6 plus x plus some numerator b over 6 minus x. Okay, so if we had those fractions originally, okay, if we're going to bring them together, we would cross multiply, which means we'd end up with a outside of 6 minus x plus b outside of 6 plus x, okay, all over our 6 plus x, 6 minus x, okay. And then what we can do is we can expand out our brackets and collect like terms. Now I'm just going to put two steps together here. When we do that, what we do is we bring all our x terms together, and that means we can write it as 6x outside of b minus a, and we get all our terms without x, okay, which gives us 6 outside of a plus b. Okay, and that would again be all over our 6 plus x, 6 minus x. And what we need to do at this stage is to equate our numerators. So you can see we've got our original up here. Okay, now we're in this form. So what we want to do is equate our numerators because our denominators are the same. So what we do is we say, well, 6x outside of b minus a plus 6 outside of a plus b is equal to 12. Okay, and what we do now is we equate our parts with x in here with parts with x over here and constants here and constants here. So you can see we've got no term in here with x in it. So what we do is we say, well, our coefficient here, okay, is our b minus a. Okay, well, that's got to equal 0, and our 6 times our a plus b has to equal 12. Okay. So you could have done 6x outside of b minus a equals 0 divided by 6x to get rid of it. We can go straight to this form here. Okay, that means that we've got two unknowns and two equations now. Okay, we're doing some substitution. Okay, we find that b equals 1. Okay, and we'll find that a also equals 1 by solving them simultaneously. Okay, so that means then that our integral can now become, well, we have a look back at this level here. Okay, is where we want to be looking and saying, well, we've got a, which is our 1 over 6 plus x, okay, plus our b, which is also 1 over our 6 minus x dx. Okay, is what we can do. So that means now that we can integrate, okay, and it means then that when we integrate that, we end up getting log to the base e of the modulus of 6 plus x plus log to the base e of 6 minus x. c. Okay, so the main part that's difficult with these is remembering our partial fractions. Now, if you're having a bit of trouble remembering that, you can look back at my tutorial on our use of partial fractions. So keep moving on. So we're looking at worked example 34 now. Okay. So again, what we're going to do is factorise the denominator here. We're saying that we've got x plus 10 going to be over x plus 3 and x minus 4. Okay, so if we were to split that, then we'd end up with, and I've written it around the other way here to what they had in the textbook, so I'll just do it back the way that you've got it. So you say, well, we're going to get a on x minus 4 plus b on x plus 3. Okay, multiply across, we're going to get a outside of x plus 3 plus b outside of x minus 4 all over our x take 4, x plus 3. Expand our brackets, we're going to get ax plus 3a plus bx take 4b all over our x take 4, x plus 3. Okay, we can bring together our like terms. Okay, and say, well, then we're going to have x outside of a plus b. Okay, then going to be plus 3a minus 4b all over our x take 4, x plus 3. Okay, now if we look at just our numerator, then we say, well, we've got our x outside of a plus b plus 3a minus 4b, and that's got to equal our original numerator, which was x plus 10. Okay, so what we do now is equate our coefficients, our same terms with x and our same terms without x. So we can say, well, x outside of a plus b equals x, so that a plus b equals 1. Okay, and we also get that 3a minus 4b is equal to 10. Okay, when we do that, again, I'm not going to go through the steps of solving these two equations, but you've got one equation there and your second equation there. Okay, if you solve them simultaneously, you find that a equals 2 and b equals minus 1. Okay, so now we can use these values back in this equation here. Okay, so we get our integral of a, which is 2 over x take 4 minus 1 over x plus 3 dx. Okay, now it's just simply a matter of integrating it, which means we end up with 2 outside of log to the base e of the modulus of x minus 4 minus log to the base e, okay, of the modulus of x plus 3 plus c. Now you're probably looking and going, can we use our log laws and things like that? Well, we could, but we don't need to worry too much, but they do show us what it would look like, which is log to the base e, okay, of, we've got our x minus 4 squared, because it could bring our 2 up, over our x plus 3 plus c. Okay, if you left it at that, okay, and didn't go to this, would you lose a mark? No, you wouldn't. Okay, so that's fine. Okay, we'll keep moving on. So we can also have examples where we've got perfect squares. So we'll look at worked example 35. Okay, which is integrating 6x minus 5 over 4x squared take 12x plus 9. Okay, so what we do with that one, okay, is we can look at our denominator. Okay, that is actually a perfect square of 2x minus 3 squared. Okay, so what that means then with our partial fractions, okay, is we set it up, okay, instead, so it's a over 2x take 3, okay, plus b over 2x minus 3 squared. Okay, it's just the way it works with these ones in terms of the way we set it up, that we have one term that's squared and one term that's not squared. Okay, so then if we were going to make these the same, we need to multiply our a by 2x take 3. We'd have just plus b over our 2x take 3 squared. Okay, which means we can say we've got 2ax minus 3a plus b, okay, over our 2x minus 3 squared. Again, we can compare to our original denominator. Okay, that means that we've got our 2ax equaling 6x. Okay, divide by x means we get 2a equaling 6. Okay, which means we can also do our minus 3a plus b is going to equal minus 5. Okay, we can see rearranging this, we're going to get our a equals 3. Okay, when we sub a equals 3 into there, we get that b equals 4. Okay, so then what we can do is put our a and b value back into here. So we integrate, a was 3, so it's 3 over our 2x minus 3 plus our b, which is 4, over our 2x minus 3 squared dx. Okay, when we integrate that, okay, then we're going to get 3 on 2 log to the base e of the modulus of 2x minus 3 minus 2 over 2x minus 3 plus c. Okay, so again, still working with partial fractions, but it's our example of a perfect square. Okay, so we'll have a look at worked example 36. So this is an example of rational functions involving ratios of two quadratic functions. Okay, so what we need to do for this one is we actually need to look at doing long division. Okay, and what they do is they do it a little bit differently actually. So what they do is they go, well, we know that we need to get this term in there. So if we go 2 outside of x squared plus 3x minus 4, okay, then if we expand that out and compare it to what we've got already, it means that we also need another 11, and we need to take away an x. Okay, and that's all over x squared plus 3x minus 4. Okay, so it looks a little bit odd doing that, but it works out nicely then, because what we can do is think of splitting these into separate fractions. Okay, and so if we split it into a fraction over here, well, this part's going to cancel out with that and leave us with 2. Okay, I'm going to be left with this as our remainder of 11 minus x over our x squared plus 3x minus 4. Okay, and then we can get into our partial fractions work, so we can say, well, that's equal to 2 plus our 11 minus x over, we can factorise this to get x minus 1 and x plus 4. Okay, which means we get 2 plus a over x minus 1 plus b over x plus 4, which means we get 2 plus our, we multiply across, okay, then we're going to get our a outside of x plus 4, okay, plus b outside of x minus 1, sorry, minus 1, all over our x minus 1, x plus 4. Okay, we can simplify that. We can expand our brackets and collect our like terms, which means we get 2 plus x outside of a plus b plus 4a minus b. Okay, all over our x take 1, x plus 4. So again, we compare this to our original numerator of 11 minus x. okay, and match up our coefficients. Okay, so we'd say our x outside of a plus b is equal to negative x. Divide by x, we get a plus b equaling negative 1. Right, and we'll also get 4a minus b equaling 11. Right, when we solve those simultaneously, we find that a equals 2 and b equals negative 3. Okay, so we can put those back in here now and say that we've got 2 plus our 2 over x minus 1. Okay, take 3 over our x plus 4. Okay, and we need to integrate that with respect to x. Okay, well, we simply get our 2 going to 2x. Okay, plus we get 2 log to the base e of the modulus of x minus 1 minus 3 times log to the base e of the modulus of x plus 4 plus our c. Okay. Again, we can actually bring these together, okay, our log parts, and say that we've got then 2x plus log to the base e. Well, our 2 can come up and make it x minus 1 squared, okay, over our x plus 4 cubed plus c. Okay, so we're getting there. We've got one more worked example to do, okay, which is worked example 37, which is about rational functions involving nonlinear factors. Okay, so we've got, this time we're integrating, and this one looks a bit yucky, that we've got x squared plus 7x plus 2 over x cubed plus 2x squared plus 4x plus 8 with respect to x. Okay, so what we need to do is, first of all, find a factor of our denominator. Okay, and we find that x plus 2 is actually a factor. Okay, so we can actually factorise our denominator. So we get x squared plus 7x plus 2. Okay, and we find that that can be factorised to x plus 2 outside of x squared plus 4. Okay, and so what we do then is we split into our partial fractions. Now, partial fractions are a little bit different when we've got a non-linear part. Okay, so what we set it up as is a over x plus 2, because that's a linear factor, but then it's plus bx plus c over our x squared plus 4. Okay, so it's just a little bit different when we've got our non-linear factors. Okay, and then we do the same process as we would do. Okay, so we multiply across and you get a outside of our x squared plus 4 plus our x plus 2 times our bx plus c, okay, all over our x plus 2 x squared plus 4. Okay, what we do is we expand our brackets and we get ax squared plus 4a, okay, plus we get then bx squared plus 2bx plus cx plus 2c. Okay, and that again is all over our x plus 2 x squared plus 4. Okay, what we can do now is we can again collect our like terms. Okay, so we end up with x squared outside of a plus b plus x outside of 2b plus c plus 4a plus 2c, okay, all over our x plus 2 x squared plus 4. Okay, and again we can equate our corresponding parts. So we look here and we go, well, coefficient of x squared was 1, so we can set our a plus b equaling 1. Okay, our coefficient of x is 7, so we can set our 2b plus c to equal 7. Okay, and then our constant is 2, so we can say that we've got 4a plus 2c is equal to 2. Hey, again, I'm not going to go through the solving of these simultaneous equations, but you'd solve them simultaneously. Hey, and when we do that, we end up getting that we get A is equal to -1, B is equal to 2, and C is equal to 2. Okay, so that means then that our partial fraction can be split into, well, it's -1 over x plus 2 plus our bx, well, b is 2, so it's 2x plus c, which is also 2, over our x squared plus 4, and we're integrating that with respect to x. Hey, so when we look at that though, we can also go, we can separate our last terms here as well. Hey, and sorry, just give me 2 seconds. Yeah, so we can split up our last term, right, into 2 separate parts. So they've just done it a little bit incorrectly in the textbook here. Okay, because they've said C is 2, okay, but then they've used C is 3 when they've actually done it in the textbook, which isn't quite right. Okay, but what we can do is we can actually split these up as well and say, well, we're going to integrate, and they just change the order around a little bit, but I'm not going to worry. 1 over x plus 2, okay, and then we're going to have plus 2x on x squared plus 4 plus 2 over x squared plus 4 dx. Okay, and so when we do that, well, we're going to end up getting our log to the base e. So that's going to equal log to the base e of x squared plus 4, okay, minus log to the base e of our x plus 2, plus, now in here they've got 3 on 2 because they've mucked up our c value, but it'd actually just be inverse tan of x on 2 plus c. So I've done that little bit of a mistake there. So you just need to be careful with some of the worked examples at times. They've said that c was 2 and then they've used 3 all the way through. Because I didn't actually do the working out with solving them simultaneously, I'm not actually sure if c is 2 or 3. Okay, but if you go through and check here, okay, if it is in fact 2, okay, then you follow this. If it's actually 3, then follow this process with the worked example that they've got in there. Okay, so again, look, there's a bit of stuff with partial fractions that we haven't seen for a while, but otherwise there's nothing too horrible in this section.